All right, let's talk circuits. So I understand that we have deviated from what's in the book. I understand that we talked about phasors, and phasors is discussed in the book. But now we're discussing, now we're sort of this filter discussion we're having is not all in the book. And I understand if that's a little bit frustrating. However, my opinion is that the book has an oversight, like it should be talking about this stuff. And quite frankly, I think this is probably the most important stuff that we're going to talk about. So, we're going to talk about it. And I think what I'm going to do to supplement the book is today and tomorrow I'm going to find some online resources where if you actually want to read through this stuff in more detail, other than just the notes I'm providing, that you can do so. However, I do want you to kind of keep relying on our lecture notes. I'll give you some more stuff to read, and I'm also going to put together a problem set, like a homework assignment for you, that will hopefully drill you on some of this stuff. So we talked on, anyway, and once we're done with this sort of section on filtering, we'll go back to sort of following the book a little bit more closely. So what we talked about on Monday was this concept of how to build, how to design a filter, like the different kinds of filters, right? So we said there's first order and second order. And second order, there's two flavors, which are underdamped and overdamped. And we talked about like how you can filter things and like how you can calculate what the output cosine is for an input cosine. And then we talked potentially about the need for steeper filters, right? Like sometimes you don't have enough, like we said, 2 poles might not be enough. Why not do 3 poles, right? Why not do 4 poles, right? Why not have a filter that rolls off more aggressively? So what I want to do today, and probably also Friday as well, is really give you some actual, like this is real circuit design. This is how it actually works, okay? This is essentially like analog filter building 101. It's not in the book. I don't know why it's not in the book, but I'm teaching it to you. So what you're looking at here is a slide that I show in my signals class, and if you come see me for signals next year, you'll probably see it again. We'll do it in a lot more details in signals, but for today, I just kind of want to give you an understanding of like roughly how this works, so that you can at least have an appreciation for it and understand the math behind it. So what we're looking at here is a series of filters, and so you have 3 different filters: the blue, the red, and the green. And all 3 of those filters roll off. Well, first of all, they have the same cutoff frequency, which is 100 hertz. Right. So here's 10 squared. It's in hertz. There's 100 hertz. They all pass through the -3 dB point at 100 hertz. So 3 filters, all with exactly the same cutoff frequency. All right. Now, I want you to look at what happens in the stop band. Those lines are parallel. What does that tell you that they're parallel? Same slope, which means they're all rolling off at 40 decibels per decade. Okay? Same slope, 40 decibels per decade, which is always what you get when you have a second order system. Remember, a second order system, first order systems have a certain steepness to their filter roll off, and then we said that a second order system is twice as steep. It's twice as good at rejecting high frequencies. Okay, so these are all second order systems. They all roll off at 40 decibels per decade. Now, supposing I present each of these 3 filters with a 1,000 hertz signal. Which filter does a better job in rejecting that 1,000 hertz signal? We all agree that the green signal is doing a better job rejecting that 1,000 hertz signal than the other 2. It's crazy, right? So the green signal looks like we're getting a rejection of somewhere in the neighborhood of, I don't know, let's just say -45 dB. Okay? So let's see. Did I just lose the mic? So the green signal is at -45 dB. What gain is that? Can somebody help me tell me what the gain is for that? What gain corresponds to minus 45 dB? In other words, 20 log base 10 of some number equals minus 45. So can we figure that out? All right, we know that 20 log base 10 of some number equals minus 45. So we're going to take 10 raised to the minus 45 over 20 should give us our gain. .005. 005, 006? Whatever. Okay, 0056. Okay. So in other words, if I present the green filter with 1,000 hertz cosine at 1 volt peak to peak, I'm getting out a 1,000 hertz cosine. Went all the way from 1 volt at the input to 5 millivolts at the output. That's a lot of rejection. Just for comparison, let's try the red signal. At 1,000 hertz, the red signal is giving me minus 45 dB. Oh, sorry, minus 40 dB. What's that? Just 0.01? Right. And the blue signal, I'm just going to eyeball it, and let's say negative 32 dB. I'm sorry, again? 0.025. That's pretty amazing. I mean, look at what I'm telling you here. I'm giving you 3 filters. They all have the same cutoff frequency, and they're all second-order systems. They have the same number of resistors and the same number of capacitors. Okay? The same number of energy storage elements. And yet, there's almost a 5-fold difference between the green one and the blue one in terms of how much rejection you're getting. It's pretty intense, isn't it? I mean, it's like you're getting more mileage for the same stuff. Okay. Well, what madness caused this, right? What magic is behind this? So, are these filters, I mean, is it good? Do I want? Is it always better to use the green one than, let's say, the red one or the blue one? So let's do this. I want to zoom in. I want to look, instead of at the stop band, I want to look a little bit at the pass band. So what do you notice? What's going on with that green signal? What's that? It goes, wiggles. See how the green signal wiggles? It goes down and up. So I really don't want to get into the specifics of this. I mean, there's we could do like a month on this. We're not going to do a month on this. I just want you to sort of get it, just put that seed of curiosity in the back of your mind. So there's all these cool trade-offs you can make when you do filter design. And one trade-off you can do is you say, okay, I want my, you say, okay, pass band, I'm willing to let my pass band mean that my signal can't get any smaller than negative 3 dB. Okay, that means 0.707. So as long as my signal doesn't get any smaller than negative 3 dB, I'm willing to say that that's acceptable for pass band behavior. So let's say the red signal is nice and smooth. You get really nice, you're passing every frequency with really high fidelity in the pass band. Okay? The green one is a little different. The green one, you're saying, well, some frequencies I'm going to have, they'll be 3 dB down, and then other frequencies will be 0 dB. They'll all get passed, but they'll just be passed a little bit differently. So the difference is if your application can tolerate having a little bit of wiggle in the pass band, right, treating some of those pass band frequencies a little bit differently, if you can tolerate that, then the math says that in exchange, you can have better rejection in the stop band for free. Kind of zany, right? So, message number one from today's lecture is not all filters are created the same. All right? How you design your filter makes a difference. Okay? And again, right now I'm just doing this for a second order filter. But it shouldn't surprise you that I can do this for any order, right? I can do a third order, fourth order, right? Fifth order. It doesn't make a difference. Okay? Although the effects of those poles add up a lot more. Like if this is a fifth order filter, holy cow. Like you can see the difference between the green and the blue is like night and day now. It's not even close. You're really getting a lot more performance, but still you have to be willing to tolerate these like slight variations in how each frequency is passed in the pass band in order to get that extra performance in the stop band. Okay, so when you come to signals, we'll learn more about how you design these filters and why you design these filters and like what's the pros and cons of each method. We'll do that for days. Okay, but today I just want you to realize that that's kind of what's going on. Now, in order to appreciate what went on in the top plot, you got to look at the bottom plot. The bottom plot is let me go back to like a third order system. Okay, and I am going to try to make this a little easier to read. Okay, is that better? All right. So filters that you've already seen on the left-hand plot. On the right-hand plot, you are looking at the poles. Remember we talked about poles. Poles are solutions to the characteristic equation. Right? We learned that if you have a real solution to the characteristic equation, or you have a real or a complex solution to the characteristic equation. So what I want to talk about today is how you actually make one of these circuits. Like let's say, for example, I want to design the red filter. Right? The red filter has this, it's called a Butterworth filter. Butterworth filters have really nice performance in the pass band. Right? They're nice and flat in the pass band, so you're getting very good fidelity on your pass band signals. They're not so hot in the stop band. They're okay, but you could do better in the stop band, but you wouldn't get such nice performance in the pass band. Yes, sir.
Can you like daisy chain a duplicate pole into Chevy?
Yes, you could daisy chain these things all day. But I think the point I'm trying to make is so this is what we said a third order filter. So if you wanted to daisy chain the blue and the green, that would effectively give you a sixth order filter, right? A third going into a third, that's collectively a sixth order filter. My contention is you'd be better off just building a sixth order Chebyshev filter. In that case, the duplicate pole filter is just there as a placeholder. Like you never do that. That's like Mickey Mouse 101. At the very least, you would build a Butterworth filter. I mean, if you look at it, there's actually no reason to take the duplicate pole filter, because not only does it have worse performance in the pass in the stop band, but it actually has worse performance in the pass. So it's worse in the stop band and it's worse in the pass band. Right? You see how the red filter is like flatter for more frequencies? It's giving you better fidelity over more frequencies than the blue one is. So the blue one is not only worse in the stop band, it's also worse in the pass band. So nobody ever just stacks like 5. This is what you would get if you just took an RC filter and did 3 in a row of them. Like all of them having the same cutoff frequency, that's what you'd get. It would be basically the crappiest low-pass filter you could build. That's the technical term for what would happen. All right? Okay, so whatever. I don't want to get too much into detail on this. What I do want to get into detail on is, suppose we decided to build this filter. So for whatever reason, you played around with this, you decided you needed a Butterworth filter, you decided a third order filter was good enough, so this is what you want. How do we build it? How do we actually make that circuit? Right? And this gets tricky, right? Because we know the math, but we don't really have a good circuit to make this, right? So it seems like So this is my goal, basically between today and Friday, is how to build this circuit. All right? So the first thing I need is I need to know where those poles are. Is that correct? Like I need to know where these X's are, where those poles are. I'm actually just going to bury into MATLAB for a minute and see if I can actually just have it give me those numbers. It looks like let's see, H butter. Plot. Oh, I know what it is. ZPK equals TF2. Oh, really? And now, of course, I'm blanking on the correct term. Hold on. Nope. Yeah, that's what I. Oh, numerator and denominator. TF2 ZP H butter. All right, I'll. Oh, here it is. There we go. Okay, good. So it looks like, sorry about it, the poles on my diagram, I've got one at negative 628. So negative 628. I wonder what's the units of that, if that's hertz or radians per second. I bet it's in radians per second. Let's see, P of 2. And so P of 2 is minus 314 plus or minus 544. Okay, so minus 314 plus or minus 544J. So I want to build that filter. Let me just come back, look at my pole zero diagram. Let's see here. Are those numbers consistent with the plot? They sure are. Okay, so here's one. This is the one at 628, and then I've got two poles at plus or minus, so it's minus 314 plus or minus 544J. Okay? So those are my pole frequencies. All right, questions so far?
Could you do that without that?
Hand equations. I mean, basically there's a bunch of ugly equations that, like, if I taught this course 10 years ago, we would have just learned those equations. And you still will learn the equations at some point, but you just use a calculator or a computer or so. Use a tool. I mean, the tools are there for a reason. And again, like, I don't want to gloss over this. Like, this stuff is interesting and important. We're just not doing it right now. I mean, I want to sort of just focus on the circuit design part of this. Okay, so, and I'm pretty sure those numbers it gave us are in radians per second. In order to give us a cutoff frequency in hertz. Okay, so those numbers are in radians per second. So I think I'm done with the computer for now. So I want to talk about how we can actually implement this, right? And we're going to follow this up with some sort of work in lab. Okay, so this is the circuit I want to build. I need these poles, okay, at those values of omega. How do I build that? I've got I need a third order system. Now we haven't learned third order systems, have we? We've learned first and second. So what could I do in order to get one circuit that has three poles. Could I do a first and then a second? Or a second and then, could I basically just daisy chain a first and a second together? Totally. What does a first order circuit look like? An RC circuit. So could I possibly start with an RC circuit that looks like this, and I'll pick my R and C such that what? Such that they will give me this pole. Remember, an RC circuit can only give me one real pole. So I'll pick my RC circuit, I'll pick my values of R and C such that they give me a pole at negative 628. So here I want my cutoff frequency to be 628 radians per second. Don't get excited. We're not actually, well, yeah, actually this one we'll do it this way. Okay. Now, I'm going to take the output from that, and in theory, so do what with it? Now what do I need?
Second order.
I need a second order system. Do we know how to make a second order low pass filter? We do, right? Wasn't that the RLC circuit? So what did that go like? Inductor, resistor, capacitor, right? So what we would do, in theory, we're not actually going to do this because this way, as it turns out, is wrong. And I'll tell you why in a second. But in principle, what we would do is we would design this circuit such that it gave us... So would it have to be overdamped or underdamped, that circuit?
Underdamped.
Underdamped. Why would it have to be underdamped? Because I'm going to get two complex poles. Only way you can do that, underdamped system. I would need to design this so that I got two poles, so that I had two poles, S1 and S2, that were minus 314, plus or minus J540, whatever I said, 544. Okay. So, and then this would be my output. V out, V in. So, in theory, this would build me a third order Butterworth filter with a cutoff frequency at 100 hertz. Now, why ain't this going to work? This isn't going to do what we think it's going to do. There's a reason, and it's important.
The frequencies would be different because the inductor, one has the inductor and one doesn't.
No? No?
The characteristic.
I'll give you a hint. This circuit right here, this circuit does exactly this. This works. This will give you that first order pole right where you anticipate it will be. This circuit will work. We can design this circuit to give you exactly those two poles. So the problem is not the first circuit and it's not the second circuit. It's the combining. Why does the combining matter? Because of the what? What about the output of the first one?
Different volume.
Right. So it's a bit, what were you going to say? No, I didn't want to jump to the answer without hearing you. Not the frequencies. So it's tricky. But I think it's a point that we've talked about before as well. When you design this first circuit, you're making an important assumption, which is that all the current that goes through here does what? Goes down, right? Our analysis, our ability to pick R and C to give you this value, depends on this current being true, right? As soon as you do this, now some of the current that goes through that resistor is going to head that way. Meaning that this guy, he'll still be a low-pass filter, but it's going to be a bear to figure out exactly what his characteristics are, because it's going to be very complicated now to tell what goes where. Now, you could figure it out. You could just do one great big circuit analysis You could use your impedances, like your phasor notations, and you could get a transfer function for V in to V out, and you could actually answer that question. But it turns out that's a sloppy way of designing this, right? Because what if I came back to you and I said, you know what? Third order system's not going to work. I need a seventh order system. Okay? What are you going to do this like with 7 filters now all daisy chained together and each one pulls off the other one? It's a poor way to do it. What would be awesome is if we had a way of saying, okay, like I need a pair of poles at this location, this circuit makes it for me. And I can daisy chain whatever I want after it, and that's not going to affect this circuit. So I need a way of like separating these circuits so that they don't affect each other. Buffer. That's one way I could do it. Everybody remember the op-amp buffer? So one solution, which nobody uses, but it will work, is I could go between these guys and do, oh, this has to be connected. I could do that. Will that solve my problem? Yes. Okay, do you see the difference now? All the current that comes from V in through this resistor goes where? Down. None of it can go in the op-amp. So you've effectively isolated the two stages from each other, but you've still, so no current goes through, but the voltage passes through, right? The buffer says that whatever this voltage is, this voltage, like that's the same voltage. That's what a buffer does. So you've effectively solved the problem. So this is awesome now. Now you can have a 7th order filter. And all you got to do is at each stage, design a filter to give you a pair of poles, which is not awful. And you can basically get yourself to where you want to go. Turns out, for a variety of reasons, although this will work, this filter topology isn't very popular. People don't really use this very much. And one of the reasons is, and I don't really know why, but it's not very common to work with inductors. So what we're going to do instead is I'm going to teach you a different circuit topology, which is uglier, but a lot more useful and a lot more common. So we will accomplish like 2 things in one go. Step 1 is we will get to practice circuit analysis on an ugly circuit. Benefit number two is you'll learn something useful. Okay? And step number 3 is it's just a little bit more practical, right? So you can actually go and make this in lab. So what if instead, so for my 2nd order circuit, instead of doing the inductor, resistor, capacitor, what if I gave you think I can do it right on the first try? Yeah. And to make life simple, because I'm a reasonable guy, we're going to presume that the 2 resistors have the same value and the 2 capacitors have the same value. I doubt anyone would have seen it before, but has anybody seen this before? This is called a Sallen key filter. It happens to be a low-pass implementation of a Sallen key filter. There are high-pass Sallen key filters. There are other kinds of filters, but it's pretty straightforward. All right, it's pretty easy to manage, and it's got some nice properties that the inductor circuit doesn't have. It uses an extra element, but we're going to find out that it's worthwhile. So what I'd like to do is to use our phasor math to calculate V out as a function of V in. We got this? Let's do it. Okay. All right, game face. All right, so first thing we need to do is we need to label all of our nodes, because I'm going to do a nodal analysis. So there is some good news. If this is V out, what should I label this node? V out. Everybody see that? This is a buffer. Therefore, if this is V out, this is V out. So that's nice, right? I've got two V outs. Okay, so that means I just need a name for this node. I'll call that Vx. That's an intermediate node. We will get rid of it shortly. So let's start with this current. All right, so what can I say about that current? Right. V in minus Vx over R. Okay, so that's that current. And what does it have to equal? It should equal this current plus that current. Okay, so let's start with this current. What does that current equal? Vx minus V out over R. Plus, I need the upstairs current, which is going to be Vx minus V out divided by the impedance of the capacitor, right? It's just divided by, like, just think of this as a resistor. If it was a resistor, it would be Vx minus V out over the resistor. But it's not a resistor, it's a cap. So we're just going to do the impedance, the resistor, the impedance of the cap. And the impedance of the cap is 1 over j omega c. And I'm going to use my little shorthand. Instead of j omega, I'm just going to say s. Right? Remember that was a shorthand we talked about? Yes, sir?
I know the R's are the same, but can we just label them just so I can identify the breakout, R1, R2?
Okay, well, if that was R1 and this was R2, this would be R1 and this would be R2. And if this was C1 and this was C2, this would be C2. Okay? All right, so one equation, three unknowns. Not loving that. Well, actually, V in is known, right? V in is we say that is known. Okay, so I've got one equation, two unknowns, V out and Vx. So I need another equation. Where am I getting my other equation from? Right, we need to do this current equals this current. All right, so how do I work that? Vx minus V out over R2 equals V out over 1 over, right, so this current equals this current. This current's easy. This current is V out over the cap impedance, where the cap impedance is 1 over j omega c. Okay. Now, step 1, do not panic. Step 2, we only need to do this once, right? If you do it once in terms of generic variables, then you never have to do it again. You just look it up in a book. But we're learning, so we're going to do it. So here's my strategy. I'm going to take my second equation. I'm going to solve my second equation for Vx. I'm then going to take that definition of Vx and sub it back into the first equation. When I do that, I will have one equation that only contains V in and V out, and a bunch of resistors and capacitors. Shall we do it? Let's do it! Okay, so, all right. First thing I don't like about this equation is all this nonsense in the denominator. So why don't I get rid of all this stuff in the denominator by multiplying through by R2? So if I do that, this bottom equation will be Vx minus V out equals S. I'm just going to drop the subscripts now just because otherwise it's going to get ugly. So S, R, C. I'm just going to drop the subscripts because we're going to assume they're the same. Times V out. Are we good? Okay. And let's get this. So Vx equals V out times 1 plus SRC. So far, so good? Seriously, I'm probably going to make a mistake at some point, so keep your eyes open. You should have seen the mess I made in signals this morning. Okay, so I've accomplished my goal for the second equation. I solved it for Vx. Now, before I substitute in for Vx upstairs, it would probably be nice if I collected all my Vx terms together, so that I only have to do one substitution instead of 3 of them, right? So let me just simplify the top equation a little bit. I'm going to multiply through by r. So that's going to give me Vin minus Vx equals Vx minus Vout plus SRC Vx minus Vout okay, and let's get all my Vx's together. So Vin equals Vx times 1 plus 1 plus SRC minus, am I doing this right? Minus Vout times 1 plus SRC. Seriously, they look over my math. I'm not going to proceed till I get some thumbs up from people.
Isn't that a 3 in the first one? Because there's 3 Vx terms.
But well, this is Vx times 1, this is Vx times 1, but this is Vx times SRC. So it's 1 plus 1 plus SRC. I think we're good. So now I'm ready to take this Vx and sub it in for here. So let's try that. So Vin equals Vout SRC plus 1. That's my Vx. Vx times 2 plus SRC minus Vout 1 plus SRC. Hey, that's not awful. Right, so all I did was I took my Vx and I substituted, I did that substitution. All right, what happens now? I'm going to distribute this nonsense and then basically just collect terms. Okay, so Vin equals Vout times, okay, so S times S, so the S squared terms is going to be RC squared S squared. Is that right? Because SRC times SRC gives me S squared RC squared. Okay, now let's do the S term. I've got SRC times 1 plus SRC times 2. That's 3 times SRC minus 1 times SRC. So that leaves me with a total of plus 2 RCS. And then finally, I've got 2 times 1 is 2, 2 V naught, 2 V out rather, minus 1 V out is plus 1. It's not awful. I mean, it cleaned up okay, I guess is my point. Questions? Are you following the math? We'll only do this once. Right? Once you have the answer, you're good to go. All right, so am I ready for my final?
Your resistors and capacitors aren't the same. Math will still work out.
Yeah, you just have like
Just multiply.
double the terms. Right, you wouldn't be able to add things together quite as neatly. It's uglier, but it works. It works. It does let you have control over some more factors that otherwise you don't have ability to control. I mean, there is advantage to doing them separately, but I think for first pass we can keep them the same. So finally, V out over V in equals 1 over, so it's S squared RC squared plus 2RCS plus 1. And by convention, we almost, and so all I did to do that was I did, V in over V out, and I brought that term over to 1 over. And by convention, we always like to leave the S squared term with a coefficient of 1. So how can I accomplish that without changing my equation? Right, divide top and bottom by RC squared. So my final answer is 1 over RC squared over S squared plus 2 over RC S plus 1. No! Thank you. What do you think? Can we use this circuit? Let's analyze this. Have I lied, first of all? Do we recognize, is this a second order transfer function? Yes. Is this so what's going to be my omega naught? Sorry, your omega naught is 1 over RC squared. That's good. Sorry, your omega naught is 1 over RC, which is good. That's as we wanted it to be. What's your zeta? I mean, this term should be 2 zeta omega naught, right? So let's see if, in fact, we can use that circuit to make that low-pass filter. The short answer is we may not be able to. We may need a slightly adjusted version of the Allen key filter, which I will spare you the derivation of. But if you understand this derivation, I think you could understand the other derivation just as well. So let's try this. So how could I even start? I still need to know what values of R and C to use. I want to build a second-order standalone circuit that can give me those two poles. What do I do? Omega naught is negative 314. Close. No. Make it into polar form. What's that going to do for me?
Then the left side will be omega.
Oh, yeah. We learned that, right? Do you remember how we learned that when you have complex poles and you convert it to polar form, that what you're left with is omega naught e to the j theta, right? And then the theta was like basically set by the damping ratio, by zeta. Yeah, absolutely. I mean, essentially what we're looking for is some numbers that when you take their roots, you get that equation. Yes, sir?
So we just work our way backwards from the quadratic?
Yeah. Yeah. Absolutely. So what you could do is, I mean, if nothing else works, you know that what you've basically got is S minus pole 1 and S minus pole 2 is your denominator. Is that not true? Where your two poles are, right, where pole 1 equals minus 314 plus 544J, and pole 2 is minus 314 minus 544J. Is that not correct? I mean, if I substitute this value of p in for here, if I substitute this value of p in for here, my denominator will be 0. So that is in fact a root of my equation. So if I take this equation and I multiply it out, I'd better get my equation. Well, can I do that? I feel like there's confusion. I'm not really sure how to tackle this. I need to pick values for R and C such that if I factor this equation, I'm going to get those roots. Do I have an option?
Isn't the 314 equal to 2 zeta omega naught? So you can set 2 zeta omega naught equal to 314 and solve for
2 zeta omega naught. No, I don't believe it works that way. No.
2 omega, zeta omega is equal to minus 314.
No. What if, okay, does everyone agree that I could rewrite my denominator like this? Can we agree on that? So, what would happen if couldn't I just FOIL that? So if I FOIL it, what am I left with? S squared minus P1 plus P2 S plus P1, P2. Okay. Well, let's just compare. All I'm trying to do is take this and make it into that. So what if I did P1, if I took P1 times P2, I ought to get 1 over RC squared. Can we do that? Yeah, we can multiply P1 and P2. Right, I'm going to do it right here in MATLAB. I get 39, no, I'm getting 394K. Is that what happens when you multiply those together? How can I get P1 and P2 and multiply them by each other? I mean, I just... 230? What's 230?
oh, never mind, it's a J.
There's a J. What are you getting? 394. Yeah, 394. Right. So I'm getting that P1 times P2 equals 39478. 394. Let's just say 395,000. Right? I'm not going to lose any. We don't need to be more precise than that. Okay. If you don't know how to multiply two complex numbers, please come back on Friday knowing how to multiply two complex numbers. Okay? I'm sorry, we can't cover that in class. You can do it in the rectangular form or you can do it in polar form. Either way works. All right, so that, just by pattern matching, that has to equal 1 over RC squared. We're almost done. All right, is that going to work for me? All right, so let's see. So RC has to equal the square root of 1 over 395k. Square root What'd you get?
628.
628 what? It's got to be, RC has to be 1 over the square root of 395K.
0 by.
Yeah. I'm getting like 1.6 milliseconds. Okay? Pick a value of R. Pick a value of C. I mean, all I did was just solve for RC. So now you can pick a value of C, 1 microfarad. Pick a value of resistors such that their product gives you exactly what you want. Okay? Yes, sir.
Can you do the same for,
The middle term?
yeah,
Well, on Friday. And what we're going to find out is that there's actually a little problem with this. Not a huge problem, but it's a little problem.